We can use trig identities to solve trigonometric equations. A trig identity is just an equation that has trig functions, and it's true for all values where those expressions are defined. Now, we've actually seen examples of trig functions before this. When we looked at the previous standard, we had reciprocal identities. For example, cosecant of theta equals 1 over the sine of theta, or secant of theta is 1 over cosine of theta, or cotangent of theta is 1 over tangent of theta. In this standard, we're going to have to deal with more than just these reciprocal identities. We're going to have to deal with Pythagorean identities, quotient identities, and other reciprocal identities. The ones that I have highlighted here are the ones that are given to you on the test. The other ones are ones that you are going to need to know. Starting with our Pythagorean identities, the first one, and I would say probably one of the most common ones, is cosine squared plus sine squared equals 1. With these Pythagorean identities, you need to be able to recognize them in other forms. One example would be if I were to subtract cosine squared from both sides, I would have another form of this Pythagorean identity, which would be sine squared of theta is equal to 1 minus the cosine squared of theta. I could have subtracted sine from both sides, leaving me with cosine squared theta is equal to 1 minus the sine squared theta. These are the same Pythagorean identity, just written in different forms. You can do the same for each of the other Pythagorean identities too. In the second identity, we have tangent squared theta plus 1 is equal to secant squared theta. So if I were to subtract 1 from both sides, I would have tangent squared theta is equal to secant squared theta minus 1. Or if I were to subtract tangent squared from both sides, 1 would equal secant squared theta minus tangent squared theta. I can do the same thing with the last one as well. Isolating cotangent squared theta would mean that it would be equal to cosecant squared theta minus 1, or I could get 1 by itself by subtracting cotangent squared theta from both sides. So cosecant squared theta minus cotangent squared theta is equal to 1. The purpose in knowing these different forms is that we can now substitute in and use them to solve equations. Let's take a look at that in the very first problem here. We have finding sine of theta if all that we know is that cosine of theta is equal to 1/3. This is not an example where we can just say that the top one is the adjacent, the bottom one is the hypotenuse, and then use a Pythagorean theorem to find the opposite and go about our way. Instead, we have to use our identities to be able to solve this. In this particular direction, it has also asked us to solve it with a specific interval. It is said that it only wants to know what is it between theta values of 0 and pi over 2. Remember that 0 to pi over 2, if we think about our unit circle, we had 0 over here and pi over 2 was up here. So we only want to know values from here to here that would be solutions to this problem. So we need to figure out what identity could I use to solve number 1. So we are trying to find sine squared and we are only given cosine. So we want to look at the identities to see which ones have both a sine and a cosine in them. And the only one that does that is our Pythagorean identity. Our Pythagorean identity is cosine squared theta plus sine squared theta is equal to 1. Well, we can replace cosine with 1/3. So we would have 1/3 squared plus sine squared theta is equal to 1. And now we can use our algebra skills to isolate and get sine alone. So we'll square our 1/3 and we get 1/9. We can subtract 1/9 from both sides. And then we need to get rid of our square. So we will square root both sides, square root the top, square root the bottom, so that sine of theta is equal to, we have plus or minus the square root of 8. Now 8 can be broken down with a factor tree into 4 and 2, 2 and 2. So we will have 2 square roots of 2, and square root of 9 is just 3. Now we know that because I square rooted both sides of an equal sign, I had to put the plus or minus. But we know that we only want values from here to here. This means that I don't need to include any of the negative values. I only have to include the positive values. So sine of theta is equal to 2 square roots of 2 over 3, because all of our values in this first quadrant are positive for sine. Number 2, it wants us to find cosine of theta if sine of theta is equal to 2/5. Once again, the trig identity that connects sine and cosine together is our first Pythagorean identity right here. So we'll start by writing that identity. Cosine squared theta plus sine squared theta is equal to 1. We were given that sine of theta is equal to 2/5, so we can replace sine with 2/5 and square it equals 1. 2/5 squared is 4 over 25. Then we can subtract 4/25 from both sides, and we'll have cosine squared theta is equal to 21 over 25. Then we'll need to square root the top, square root the bottom. So cosine of theta is equal to square root of 21 over square root of 25, which is 5. 21 cannot be broken down any further with our factor tree because it's two prime numbers multiplied together. Once again, we are dealing only with this first quadrant here, and everything in this first quadrant has a positive cosine value and a positive sine value. So we don't need the plus or minus sign with this one either. Number 3, it's asking us to find secant of theta if tangent of theta is equal to 4/5. So if we look back at our identities, the one that connects secant with tangent is right here. So we can rewrite this using that identity. So we will have tangent squared theta plus 1 is equal to secant squared theta. Tangent is 4/5, and we'll square it. 4/5 squared is 16/25. And 16/25 plus 1 gives me 41/25. You can just type it into your calculator. And that equals secant squared theta, but we want to know what is secant. So we'll square root both sides, square root the top, square root the bottom. So secant of theta will equal square root of 41. 41 is prime. Square root of 25 is 5. Remember that secant of theta is equal to our 1 over cosine of theta. And since cosine is positive in this quadrant, secant would also be positive in this quadrant. So we do not need a plus or minus sign. This will be our answer. Number 4, find cotangent of theta if we know cosecant of theta is 7/5. Once again, look over your identities and decide which one relates cosecant with cotangent. That identity is our third Pythagorean identity. So we can start by writing that identity. Cotangent squared theta plus 1 is cosecant squared theta. We know that cosecant is 7/5, so we can replace that. 7/5 squared is 49/25. Then we'll subtract 1 from both sides. 49/25 minus 1 gives me 24/25. Then we'll square root both sides. Square rooting the top means that I'm gonna need a factor tree. 8 and 3, 2 and 4, 2 and 2. I can take a pair of 2's out. So cotangent squared theta is equal to 2 square roots of 6, because 2 times 3 is remaining. Then the denominator, the square root of 25, is 5. Cotangent is cosine divided by sine. And if we look back at that original quadrant, both cosine and sine are positive. So when I divide them, they would still be positive. So I do not need to have a plus or a minus sign there. Number 5. Using these trig identities, we're going to find the value of the expression, but this time we are going to use the interval pi to 3 pi over 2. So let's locate where that is on the unit circle. If this was my unit circle, pi is right here, and 3 pi over 2 is down here. So we are looking for the values from here to here, right in that third quadrant. So our cosine in that third quadrant is negative, and so is our sine in that third quadrant. Looking at number 5, it wants us to find sine if we know cotangent of theta is 3/2. Well, we don't have an identity that directly connects sine with cotangent, but we do have an identity that directly connects cotangent with cosecant. And that identity is cotangent squared theta plus 1 is equal to cosecant squared theta. The reason why it's okay to connect cotangent squared theta with cosecant squared theta is that cosecant is one of our reciprocal identities. Cosecant of theta is equal to 1 over the sine of theta. So if I can connect cotangent with cosecant, then I'm really connecting cotangent with the sine of theta. Cotangent of theta is 3/2. So 3/2 squared plus 1 is equal to cosecant theta. 3/2 squared is 9/4 plus 1. And then 9/4 plus 1 is equal to 13/4. And then we can square root both sides. Square root of 13 cannot be broken down, but the square root of 4 is 2. So I have that the cosecant of theta is equal to the square root of 13 over 2. That means that the sine of theta would have to be the reciprocal of that, 2 over the square root of 13. Rationalizing that would give us our final answer of 2 square roots of 13 over 13. And let's think about what sine is in that quadrant. Sine is negative, so this will have to be negative. For number 6, we want to know what is secant of theta if sine of theta is equal to negative 2 over 3. And we don't have an identity that directly relates sine to secant. We do have an identity that will relate sine to cosine. That identity is cosine squared theta plus sine squared theta is equal to 1. The reason why it's helpful to relate sine to cosine if I'm really looking for secant is because cosine and secant are related. Cosine of theta is equal to 1 over secant of theta. So if we know that sine is negative 2/3, then cosine squared theta plus negative 2/3 squared is equal to 1. So cosine squared theta plus negative 2/3 squared is positive 4 over 9. Then we can subtract 4/9 from both sides. So cosine squared theta is equal to 5/9. And then we can square root both sides, square rooting the top, square rooting the bottom. Cosine of theta is equal to square root of 5, which can't be broken down, and the square root of 9, which is 3. Cosine in this quadrant is negative. Therefore, I'm going to keep this as negative. So when I rewrite this as secant, I know that that's really the reciprocal of what I have here. So secant of theta is equal to negative 3 over the square root of 5. Rationalize that by multiplying by the square root of 5 over the square root of 5. And my final answer is negative 3 square roots of 5 over 5. Number 7, find cosecant of theta if secant of theta is equal to negative 2. We do not have an identity that directly relates secant and cosecant. However, we do have an ability to change cosecant and secant into sine and cosine. And that's helpful because we have an identity that relates sine and cosine together with one of our Pythagorean identities. We know that cosecant is really 1 over sine. We also know that secant is really 1 over cosine. And if I keep those in my head, I can use the identity cosine squared theta plus sine squared theta to relate these. Secant is 1 over cosine, so if secant of theta is equal to negative 2, that would mean that cosine of theta would have to be equal to negative 1 over 2, the reciprocal of that. We can replace cosine in this problem with negative 1 over 2 squared plus sine squared theta equals 1. Negative 1/2 squared is positive 1/4. Subtract 1/4 from both sides so that sine squared theta is equal to positive 3 over 4. Square root both sides, and sine of theta is equal to the square root of 3 over the square root of 4, which is 2. And remember, in the current quadrant that they've asked us to find, our sine is going to be negative. If sine of theta is equal to this, we can now find cosecant of theta by doing the reciprocal, negative 2 over the square root of 3, and rationalizing, giving us a final answer of negative 2 square roots of 3 over 3.